Hello, in this video we're doing Lab 6, the introduction of Lab 6, which is about adders. In further videos or in other videos we're gonna do some practical work or simulation work on adders. Particularly we're gonna use Quartus to use VHDL language to program the full adder and a 4-bit parallel adder. In another video we're gonna see how to simulate the adder circuit using Logisim. In Lab 5 we're gonna introduce the basic component or the building block for the adder, which is the full adder. Then we're going to use multiple full adders to create a parallel adder. Then we're going to move on to how to create a subtractor from the full adder or from a parallel adder. Finally, we're going to implement the adder using behavioral versus structural modeling in VHDL in an additional video. The full adder, like I mentioned earlier, is the basic building block for a parallel adder. Its purpose is to add 2 bits together plus 1 carry-in bit. Just like how you do normal addition in math, when you have 2 numbers you're interested in adding, sometimes there is a carry out, and the carry out is always going to be the carry-in of the previous addition. For example, if you're adding 9 plus 8, the result would be 17. So you have a 7 and then 1 carry out. It's the same in the digital lab. The basic building block is the full adder. Since we're dealing with binary numbers, then the maximum number we can reach is 1. And if the result of the sum is 2 in decimal, that means the sum bit is going to be 1, and you're going to have 1 at the carry. The sum bit is going to be 0, and then you're going to have 1 at the carry out. We'll see further examples once we complete the truth table of the full adder. Basically, it takes 2 inputs, 2 main inputs, A and B, which are the 2 bits you want to add, and Cin, which is the carry-in bit. So you're actually adding 3 bits together using the full adder, and the results or the outputs are going to be 2. The first output is the sum bit, and the second output is the carry out bit. For example, if you're adding A, B, Cn, whose values are all zeros, then 0 plus 0 plus 0 is going to be 0 in decimal. So that means the sum bit is going to be 0, and the carry output is also going to be 0. If you add 0 plus 0 plus 1, then the sum is going to be 1 in decimal. That means the sum bit is 1, the carry out is 0. In the next row, we have the same result. The result of the summation is 1. So the sum bit is going to have a value of 1. The carry out bit is 0. Here's a more challenging example. We're adding 1 plus 1 plus 0. The result would be 2. So we're going to write number 2, but in binary, that'll be 1 from the left and then 0 on the right. That means the sum bit will be 0, and then the carry out bit will be 1. You can simply read this number in binary, which will be 1, 0, then convert it in decimal, the number or the result would be 2. So that means this is one way for you to verify your answer. If you keep that formatting of having C out on the left hand side and the sum bit on the right hand side in your truth table. So now this will complete the truth table of the full adder. Notice that the full adder has 3 input bits, A, B, which are the 2 numbers you want to add, and the carry-in bit, and it outputs 2 variables, the carry out bit and the sum. So anything in black is now the input bits or the input signals. Anything in red or burgundy is the output bits. So far, we've introduced the building block of any adder. That means if you combine more than one full adder, you can easily create an adder that can add more than one bit. Here we're using 3 full adders. For abbreviation, I used FA, so FA means one full adder. Here we're connecting 3 full adders together for us to be able to create a 3-bit parallel adder. That means an adder that can add numbers of at least 3 bits. For example, 7 is 111. It is possible for us to add 7 plus 0, for example, using this 3-bit parallel adder. Notice how the connection is happening here. Carry out of the first full adder. The first full adder, I named it FA0, or its inputs are A0, B0, so it will take the least significant bit of the numbers A and B. And it has one carry out bit. The carry out bit, we're not reading it at all. Instead, we're connecting it as the carry in of the next full adder. So CO0, or carry out bit number 0 of the first full adder, is now connected to CN1, or the carry in of the first full adder, of the full adder number 1, to be exact, to be more precise. And the same goes to the next full adder. So the full adder in the middle takes bits number 1 of A and B, and the carry in of it is the carry out of full adder number 0. The carry out of full adder number 1 now is connected to the carry in of full adder number 2, and so on. Here I'm only highlighting that CN1 is equal to C out 0, CN2 is equal to C out 1, and so on. Notice that we're only outputting the sum bits plus one main carry out, and we only have one CN bit, since the rest of the bits are all internal bits, or internal signals, if you may say. If you actually want to use the circuit that we've just designed as a parallel adder, then the first carry in is by default going to have a value of 0. Because let's say we want to add 9 plus 7, then we're always assuming that there is a carry in value of 0 at the beginning. So 9 plus 7 in decimal will be equal to 16, or to be exact, it will be 6 with 1 at the carry out. So the same goes here in digital numbers, or in binary numbers. The first carry in by default is always going to be 0. The first carry in is always going to be 0, and the rest will be as it is in the previous slide. Now this is a complete 3-bit parallel adder. We will hardwire 0, or the ground, to the first carry in, or carry in number 0. And the rest we can simply measure or read. Anything that's an output, including S0, S1, S2, and S3. Notice that I labeled the last carry out as S3. It is the last carry out, but you can consider it as the last bit of the sum, or the highest significant bit of the sum bits. So these are our outputs. We can connect LEDs, or some indicator for us to be able to read them. And regarding the input bits, we can use switches if we're dealing with a training board, or if we're dealing with a simulation tool, we can always connect switches or pins in Logisim. To a challenge or a problem that requires us to create an adder slash subtractor circuit. That means we have a 4-bit parallel adder chip, and we're required to modify the circuit or add some simple circuit and connect it to it or attach it to it so that this circuit will work, or this chip will work as an adder and subtractor at the same time. Let's read the problem statement. It says, given a 4-bit parallel adder, create a circuit that adds two 4-bit numbers when m is equal to 0. So m is an additional input. If m is 0, then the circuit will add the two numbers a and b. If m is 1, we're going to subtract the two numbers. So the result will be a minus b instead. We learned already how to create an adder and how to create the subtractor separately, but the circuit will combine both depending on the value of an additional input named m0. So let's split the problem into more details. So we know that we need a value for the carry in bit, right? And we said for addition or for any adder, the carry in bit is equal to 0. And the circuit or the question also requires us to check the value of m. If m is 0, do addition. And we learned that for adders, the Cn or the carry in bit must be 0 if you're adding. And for subtractors, we said earlier that Cn must be 1. So we can say that Cn is equal to m, right? So we've solved part of the problem. We can say Cn is equal to m, so we can connect m to Cn. Now for the rest, we said A is always going to be untouched. So X in the circuit, to be exact, we're not going to touch it, we can leave it as it is. Because if you're doing A plus B or A minus B, A is always A. We don't change it. But if we're doing subtraction, then we need to take the complement of B, right? So that means so this completes part of the solution. We said already that Cn is equal to m. Now y in the chip or the circuit here that we have, y is equal to b when m is 0, or when we're performing addition, y is equal to b as it is. And y is equal to the complement of b, so y is equal to not b when m is 1. If you are comfortable converting this statement into Boolean expression, you can easily figure out that y is equal to b and not b, and not m, sorry. Y is equal to b and not m, or b not and m. So b bar and m. So we're simply translating the condition in the middle to a Boolean expression. So we can say that y is equal to b and not m, or not b and m. If you remember, this is exactly what the XOR does. So if you have an expression that says b m bar or b bar m, then this is exactly the output of the XOR gate that takes b and m as inputs. So you can say that y is equal to b XOR m. So we will need a total of 4 XOR gates to implement the adder / subtractor for a 4-bit circuit. We'll explain this again in a different way. Remember the XOR gates truth table. So if we have an XOR gate that takes M and B as inputs, then Y will be as such. So this is exactly the truth table of an XOR gate. We said Y is equal to B when M is 0. So in the first row we have M is 0, B is 0, so Y is equal to B as it is. And then in the second row we have M is 0, B is 1, and Y is equal to B, which is 1. So this is another proof that shows that Y is actually, in fact, equal to B XOR M. And on the right-hand side, you see the XOR gate symbol and how we write it as a Boolean expression. It's like a plus sign with a circle around it. And on the training board, the symbol for the XOR gate is equals 1. Now we're connecting or creating the small circuit that we've designed, and we're going to try to sketch it on the current sketch that we have, or the current chip that we have. This is what we've solved so far. We said Cn is equal to m, y is equal to b XOR m, and we said that the first input we're going to leave untouched. I simply named it as a instead of x0. So this will complete the solution. Now this circuit is a complete 4-bit parallel adder / subtractor. So each bit in B, we XOR it with the same m that we have. This way, this will guarantee that we'll take B as it is if we're performing addition, or if m is 0, y is equal to b directly. If m is 1, we will take the complement of b. If you're still unsure, you can simply trace each case. So just give a value for m and for b, and then try to trace the output and see what it would be. Moving on to how to implement this on the training board, what you'll do is, since you need 4 bits for A, 4 bits for B, and you have one additional input, which is M, that means you'll need a total of 9 switches. Remember, we'll use switches for inputs and LEDs for outputs. So I'm just labeling the switches, each switch that I'm going to use, and I highlighted in the middle the XOR gates, and the 4-bit adder on the training board looks like such, and this is where it's located. It's on the corner of the board. And finally, we'll have 4 bits for the sum output and 1 additional bit for C out, where also we can label it simply S4. To do the connection, this is what it would look like. On the left top corner, I colored or highlighted each wire or each signal that I need to connect, and colors. So I color coded basically the circuit. This way it will be clear for me to identify what each wire represents. Now moving on to the full adder logic diagram, you can use the truth table for the full adder to generate the full adder expression. Then you can simply connect it or sketch it. So by looking at the full adder logic diagram, you can figure out the expression for it. For each of your outputs, you have S, and you can say that S is equal to A XOR B XOR Cn. We're gonna see a way to, or just a revision of the template for behavioral model expression or behavioral modeling code in VHDL. Remember, we said there is 3 parts for the code in each file. The first part is the library declaration. It consists of 3 lines for our lab. You don't have to worry about them, they're just there. You can just simply copy them, paste them. And the good thing about the Quartus, the environment that you're going to use, is that it auto-completes your code. So if you can simply type LIB and it will complete for you. So with practice, you don't have to even copy them. You can simply type the first few letters, and then Quartus will auto-complete the rest for you. So the first part is the library declaration. The middle part is where you define the entity, the name of your circuit, how many inputs, and the name of the inputs that you have, and how many bits they consist of, as well as the name and the length of your outputs. So it basically declares the circuit name and its ports. When we say port, we mean either an input or an output. Anything that's not an input or an output, we'll use the term signal for it in VHDL. This is for the middle part or the entity part. For the last part, we'll define the architecture. That means how the ports are related to each other, or what is the relationship between the input and the output of the circuit. So let's declare the entity part. We said that we'll define the ports of the circuit, right? Looking at the circuit logic diagram given here, we already have mentioned that we have 3 inputs for the full adder. So we can say port A, B, C, N. These are inputs. And the keyword for 1 bit in VHDL is standard logic. And then we also mentioned that we have 2 outputs, and they're each 1 bit outputs. So we'll say S, comma, C out, and these are output of standard logic. Again, standard logic simply means 1 bit in VHDL. This now completes the entity part of the code. Finally, we'll need to define each of our output using behavioral modeling. We said that S is equal to A XOR B XOR Cn, but remember that when we say equal, in VHDL, we have to use less than or equal to, but it's not actually the comparative operator, it's the assignment operator. So think of it as an arrow pointing towards S. So S, you can read this as S is assigned a value equal to A XOR B XOR Cn. Semicolon, don't forget the semicolon. The syntax is very important in VHDL. And Cout is another output, and it is defined as Cn and A XOR B. Remember, use the brackets or the parentheses in your favor. Sometimes it's optional to use them, sometimes it is important that you use them, especially if you want to control the priorities of the arithmetic that you want to perform. So OR is in the middle, and then you have A and B. This completes the code for the behavioral modeling of a full adder. So you can save this in a file named full_adder. Remember to always name the file name as the name of the entity. So now this is only the full adder file, and then we're gonna understand how to implement a 4-bit or a multi-bit parallel adder. So remember, the full adder is the basic building block. So think of it as a Lego piece that you'll use to build a house, or you can use more than one, depending on your need. In this logic diagram, we see, or block diagram, we see 4 full adders, and they're connected in a way that this circuit will act as a 4-bit adder. We'll simply use 4 full adders in cascade, where each Cout of each full adder is connected to the next full adder's Cn. So the Cout of the first adder is the Cn of the second full adder. Cout of the second full adder is Cn of the next full adder, and so on, until you reach the last full adder. Once we reach the last full adder, then we're going to output this as Cout of the parallel adder itself. And the first Cn will use it as an input to the parallel adder. So anything in between is going to be an internal signal. Anything that's anything that's not an internal signal, that means it's an input or an output, which means it's a port that needs to be defined in the entity part of the code. Notice that some signals in the sketch here have two names. For example, Cn1 is equal to Cout0, Cn2 is equal to Cout1, and so on. When we want to program this in VHDL, it's important that we make a decision on the naming. So I'll replace these wires with one single name. I'll choose to name it as Cout0, Cout1, Cout2, like such. So that means I will have a total of 3 signals, CO0, CO1, CO2. Remember, signals are anything that's neither an input or an output signal. Anything that's internal that I'm not outputting or inputting. And I'm using one component, which is the full adder, and I'm using it 4 times. So this will create a map for me, or a guide for me, for when I want to implement this in VHDL. One component, which is the full adder, and it is copied or instantiated 4 times, and I have 3 signals, CO0, CO1, CO2. Remember that A0, A1, A2, A3 is all just A, but it has 4 bits. So another way to look at it is that A is a bundle of wires, but they're wrapped together. So we can say that it is a cable that consists of 4 wires. So A0, A1, A2, A3 is all A, but they're part of A. So we can say that we have we have one signal for A, but A is consisting of 4 bits total. So when we summarize the number of ports that we have, we can say that we have A as a port, since A is the first input. Second input is B. Third input is Cn. Then we have S, and S as an output, and Cout as another output. So even though we have A0, A1, A2, A3, we can simply use one variable name for them, labeled A, and then we can mention in the code that A consists of 4 bits. And the way to do it is to use another syntax. Remember, we said standard logic in VHDL means 1 bit. When we indicate a multi-bit vector or a multi-bit variable, we need to say standard logic vector. And then we need to specify how many bits that vector consists of. In this slide, we see an example of what's called structural modeling code, structural modeling VHDL code. Again, it still consists of 3 parts: the library declaration, which are the 3 lines on the top, and in the middle we see the entity declaration. It's the same for both structural and behavioral modeling. The entity part, I named the entity parallel adder. I can be more precise and say this is a 4-bit parallel adder, but remember to always start with a letter. The entity name must start with a letter. And I will declare the ports, which I've defined earlier, A, B. I separated Cn because Cn is 1 bit, so I combined A with B, and I mentioned that these are inputs, and their type is standard logic vector. And the way to define their length is to say 3 down to 0. Remember, down to is one word, and then 0. You always start with the highest number, so you can count from 3 to 0. You'll have 3, 2, 1, 0, which will give you a total of 4 bits. So the highest significant bit index is 3. The least significant bits index is 0. And then the next input is Cn, but it consists of one one single bit. That's why we said in standard logic. And we use the semicolon to separate the list. Next we have cout, and cout is an output, colon out. Cout is consisting of one bit, so we said standard logic. And then what's highlighted in yellow is a missing part. So we need to figure out that the missing part is actually S. The sum bits are missing, so we need to include them. We'll simply say S, but S consists of 3 bits total, so we'll say S colon out standard logic vector 3 down to 0. Remember that always the sum bits are equal in length with the numbers that you want to add. So if A is 4 bits, B must also be 4 bits, and the sum bits must be 4 as well. The last part of the code is the architecture part, where we define the relationship between the inputs and the outputs. This is different from what we've covered so far because it introduces the structural modeling of VHDL programming. And here we have defined the architecture name. We named it struct. And it describes the architecture of the parallel adder. And then we say is. Notice that begin is not right after is. We left it till later because between is and begin is where we define any component that we are using in this file and any signal that's neither an input or an output. So anything that's not a port, if it's a port, it should be defined in the entity part. So anything that's an input or an output means it's a port that must be defined as in the entity part of the code. Anything that's internal is a signal in VHDL, so it will be defined here. According to our guide that we've created earlier, we need 3 signals, CO0, CO1, and CO2. Remember, VHDL is case insensitive, so it doesn't care if I use big C or lowercase c. It's the same. And then once we've defined the ports, the signals and the components, we can say begin and then define the relationship between the inputs and the outputs. Let's go back to the component part of the code. The syntax or the way to do it is to simply type component and then end component, and in between you list all the components that you have. I only have one component whose name is full adder. Remember, the spelling is very important here. If you named your file full adder without an underscore, make sure here you mention full adder without an underscore as well. So full underscore adder, then you copy the port file from the previous slide. So the port line of code from the previous slide, you copy it as it is and then paste it here. So you don't have to retype anything. It's important that you paste it as it is. We've done something similar in lab 3. So the structural modeling is nothing new, but here we're using it to implement something more practical. So the component is now no longer a gate, but it is actually a building block, which is the full adder. And then between begin and end is where we actually define the relationship between the input and the output. We're using the component, the full adder component 4 times, but each time you remember to give it a unique name. The first time I'm using the full adder, I'll name it FA0, short for full adder 0. And then is, the colon means is in VHDL. So FA0 is a full adder. And then the keyword port map will do the mapping for me. So instead of A, I will have A0, the first bit of my adder. So this A0 is one of the ports. It's actually a signal or the first bit in port A. the least significant bit in port A. So A0 will take the element in the zeroth index in A. So index number 0 of A, take that number, put it here. So A0 added to B0 with the first carry in. So this Cn is the carry in of the entire file. And it is important that you use the correct order. So if in your full adder you define the signals order as A, B, C, and S, C out, then even here when you do the port mapping, you must have A first, then B, C, and S, C out. So order matters a lot here. Sometimes if you miss the order, sometimes you don't get any compilation error, but you might get some logical error when you simulate the circuit in Model Sim. The code for defining the 4 full adders is missing, but you get the idea. What's missing is the definition of FA2. You simply copy the previous line and change the numbers. So it will be FA2 colon full adder port map A2 B2 CO1 S2 CO2. You just increment the number by 1. But the tricky part is the last full adder. Remember, last full adder's C out is no longer a signal, but instead it would be C out of the file itself. So whatever name you gave it, make sure you type it here at the last C out. And the first Cn is the Cn of the file itself. The last C out is the C out of the file itself. Here you're seeing practice exercises. These are optional. Feel free to implement them just to help you practice further on this lab. This will be the end of this video. Please watch the other 2 videos related to the lab, which are coding the parallel adder and the full adder in VHDL using structural and behavioral modeling. And the other video is to simulate the circuit of the full adder and the parallel adder / subtractor circuits. Thank you for watching. Please email me at alatia@auk.edu.kb if you have any questions. Thank you.